Anything you can do in linear motion, you can do in rotation. So we've said that when there is an impulse on a system, right, some force average acting over some time, it leads to a change in a quantity that we called momentum, right? And momentum here was m times v. So what if we think about a torque acting over some time? Well, a torque acting over some time also leads to a change in momentum, but it's a different kind of momentum. All right, and it turns out we can define that momentum as I times omega. It's the same derivation, same idea. Um, this is what we call angular momentum. And again, it's just momentum of something that's rotating, right? So one way to talk about momentum is it's an object's momentum is how hard it is to stop, right? So we could say a very fast light object could be hard to stop. A mediumly fast heavy object is also hard to stop, right? Could take the same momentum change to stop each object depending on the math. Same thing here. Angular momentum is how hard it is to stop something from rotating. um, so so this is one definition. I times omega. The other definition is if we have a point mass. All right. So I times omega is useful if we have a like a disk, right, with some radius rotating at some omega, or we could have some like solid rod with a length L rotating around its axis of rotation. But we can also define angular momentum for a point mass, right? So if I have a point mass, let's say this is my axis of rotation, and I have an object with a velocity right here. So what's the angular momentum of this point mass around this axis of rotation? Well, there's an r here, right? That's the distance from the axis of rotation to the object. And there's this velocity. And for point masses, I know... let's do this. For point masses, I know I is mr squared. And I can also say, well, omega is related to v, right? So it's v over r. But it's not all of the velocity. Remember, omega relates to tangential velocity. So I need to say that's v tangential over r. Let's make it a lowercase r. Okay, so v tangential is just the part that's tangent to the circle defined by the radius. All right. Again, the object's not traveling in that circle, but only the velocity that is tangent to that path contributes to this. So, okay, I can define an angle here, theta. It's the same as the angle here, theta. So it looks like v tangential is v sine theta. So the other thing the other way I can define angular momentum, if for a point mass, is I just said I was mr squared, and omega is v tangential over r, which is v sine theta over r, which gives me an mvr sine theta. So there's the other definition. So I've got that definition and this definition. They're both true, they're just useful in different cases. So if I have an extended body, like a like a solid sphere or a disc or a rod, I'm going to use I omega. If I have a point mass, I'm going to use mvr sine theta. Let's do an example where we do both of those. So I'm going to look at Example number 12 here. So here we see a uniform thin rod with a length and a mass, and it's allowed to rotate about its center. And we shoot this thing with a bullet. Obviously, we shoot this with a bullet. So when we fire a bullet at this, the system's going to start to rotate. All right, and if there's very little friction in the axis, even if there's a little bit of friction, I expect momentum to be conserved just before and just after. Right afterward, it might slow down, but I expect momentum to be conserved here because the interaction force between them is an internal force. There are no external forces on the system, at least anything that's appreciable over the time of just before and just after the collision. This is very similar to saying one block hits another block and they stick together and leave the collision. This is a perfectly inelastic collision. All right, so I'm going to use conservation of angular momentum. This is just conservation of angular momentum. Which is just L initial equals L final. And often for total, we say L as a capital. But it's really just going to be L for the rod initial plus L for the bullet initial equals L for the rod final plus L for the bullet final. Okay, so initially all I have is the bullet because the rod's not rotating at all, right? And finally, right, at the end, I have these two things rotating together with the same omega. And that's what we're solving for, is omega final. Okay, so let's label a couple things here. So I have a V initial right here. I have a radius for his angular momentum. So for that term, we'll do this. For that term, I'm going to use mRV sine theta. All right, that theta is 60 degrees. I'm given that. V is, I think we're given that. Oh no, that's what we're solving for. Awesome. So V initial equals question mark. That's what we're looking for. But I know omega final. So after this hits this, so let's, this is my before picture. My after picture is the rod, the bullet lodged right here, and the whole thing rotating at omega final. Right. Okay, and omega final is given to me as 10 radians per second. So I'm solving for V initial. Okay. So so we're halfway there. We filled in the left-hand side of this equation. Again, this term is this entire thing here. MRV sine theta. We're just using the MRV sine theta definition for this. So R is half the length of the rod. So let's write that down. Half the length of the rod is 0.25 meters. The full length of the rod is 0.5 meters. I'm going to call that capital L. The mass of the rod is 4 kilograms. The mass of the bullet was 3 grams. So 3 times 10 to the minus 3 kilograms. Okay, we're close. We're close. So we did the left-hand side of conservation of angular momentum. On the right-hand side, I'm going to say I times omega final for the rod plus We can do an MRV sine theta, but now that it's stuck in the rod, I'm going to call it I for the bullet, omega final. Where I for the bullet is now MR squared. Right? I could still use the MV, the MRV sine theta definition, and it'll give me the same answer. V will now be a tangential velocity. I would actually want to relate that to omega, so it would be V equals omega times R, which would be an MR squared, and theta would now be, because V final is now this thing, theta would now be 90 degrees. But now that it's stuck in the rod and rotating in an actual circle, I think I omega is a better way to think about it. Okay, so I'm going to come down here and do the next line. So let's do this. MR V initial sine theta. Those are all numbers that I know except for V initial, which I'm solving for. I for the rod. This is a uniform rod rotating about its center. So I have that equation. It's 1/12 ml squared. Right? This one right here. So 1/12 ml squared plus mr squared times, oops, I missed a term. That's just I there. I also need to put omega final in there, plus mr squared omega final. Okay, I think we're ready to plug numbers in. So the mass of the bullet is 3 times 10 to the minus 3 kilograms times the radius of the rod is 0.25. It's not really a radius of the rod, right? But it's the it's half the rod length. It's R for the moment of inertia, the angular momentum of the bullet. V initial is what I'm solving for. Sine of 60 degrees equals 1/12. The mass of the rod is 4 kilograms. The length of the rod is half of a meter squared times omega final is 10 radians per second. Plus 3 times 10 to the minus 3. That's the bullet mass times 0.25 meters squared times 10 radians per second. Okay, that's it. So if we solve for V initial, what we get is 1,286 meters per second. Okay, which is not correct to the sig figs, but that's good enough. Okay, that's pretty darn fast. It's a little bullet, though. So we could ask one more question about this. We could ask all sorts of questions, but we could ask how much energy is lost. How much energy is lost in this? Okay. Do I expect energy to be lost? Well, it's perfectly inelastic. So inelastic means energy is not conserved. Right? So we could answer that question if we have some space here. Basically, what's delta K? Right? Well, K initial is half mv squared for the bullet. Right? So we could solve for that. Half 3 times 10 to the minus 3 times the 1286 that we just found. What I get for the kinetic energy of the bullet initial is 2,480 joules. K final is both of those objects now rotating. So I'm going to say half I omega final squared for the rod. Oops. We can even do rod. Plus the same thing, half I omega final squared for the bullet. So half 1/12 ml squared times omega final squared plus half mr squared omega final squared. Again, we have all the numbers for that. In the interest of saving space, I will simply say if you plug all those numbers in, you get about 4. So 4 0.176 joules. So we lost almost all of the energy to probably heat and the work it took to deform the rod. Maybe the work it took to deform the bullet, if the bullet deformed. Right. So again, we see momentum can be conserved even when energy, at least mechanical energy, is not conserved at all. Yeah. So let me talk about one other thing here. There's another way to talk about conservation of angular momentum. And that is, instead of like two objects colliding, we could talk about an object simply redistributing itself. And that's this. So when we said linear momentum is conserved, P initial, P final, that's like mv1, m1v1 plus m2v2, etc. equals, these are all initials, equals m1v1 final plus m2v2 final, etc. If we only had one object, this was really boring. m1v1 initial equals m1v1 final. This is really boring because, there's the mass initial and final are presumably the same, so v1 and v2 are exactly the same. But now that we're thinking about angular momentum, if I think about a single object, I could say I initial omega initial equals I final omega final. And remember, moment of inertia depends on mass, but also how that mass is distributed. Right? So if a system changes its mass distribution, it can change its angular momentum. Sorry, its angular velocity, because of conservation of angular momentum. Think about a figure skater, right? So a figure skater who is spinning, let's say, has her arms and one of her skates out a little bit. So how do you draw that? Let's see. Arms out. Long arms, that's fine. And one skate out. So there's a skate out and there's a skate on the ground. And let's say she is rotating with some omega initial. Now let's say she pulls her arms and her skate in. So that skate is in and her arms are in. What do I expect to happen? So there's some omega initial, omega final. Omega final is now smaller than omega. Sorry, I say omega. Her moment of inertia is now smaller than it was, right? Because more of her mass is closer to the axis of rotation. The axis of rotation is simply straight down the center here. Right, so if omega final is smaller than, if I final is smaller than I initial, in order for this to be true, her omega final has to be bigger than omega initial. And, Google this. This is exactly what happens if you've never watched figure skating. Figure skaters can get to incredible angular speeds by reducing their moment of inertia by pulling in their arms and their legs. And that's just conservation of angular momentum. So we'll see more examples of this in the very near future.